Hello and welcome to chemistry. So what we're going to talk about today are the elements, one of the first theories of matter. And as a reminder, chemistry is the science of matter. So when we started looking at the universe around us and thinking about what all this stuff is, all the things that occupy space and have mass, trying to put some logic to it, one of the first theories that we talked about was the theory of elements. And under the theory of elements, in its original form, we decided there were four fundamental substances: air, earth, water, and fire. Those elementary substances, we later found that one of them was actually a reaction. Another was a mixture of substances. One was a compound. Only one of those four still stays on the periodic table. Actually, it's now a section of the periodic table. But we'll get into this detail in a little more detail because there are varied forms of Earth on the periodic table. The periodic table today has 118 elements on it, and we're still adding to it. The last of these elements was only added to the periodic table in 2015, so we're still growing that. But let's talk a little bit about elements and what it means to be an element. So, as a reminder, we're basing our discussions. This is coming from our discussion of scientific method, and chemistry is a science, but it's got a history that predates the scientific method, or maybe deviates a little from the scientific method. So let's talk a little bit about first the scientific method, and then the history of chemistry and the history of the elements. The first thing to realize is that scientific method starts with observation. You discover new knowledge by coming at things with a humble mind, by looking and listening to the numbers and capturing your observations. And then from that, you try to imagine an explanation, a hypothesis. That hypothesis, that tentative explanation, is then improved by testing it, by looking for falseness in it. So you start with a box that seems likely to be true, and you start picking away from that box, taking out of that box everything that's false by experimentation. You compare it to reality. And anything that doesn't match reality loses. Reality always wins. And so you take falseness from that box by experiment. What happens is, eventually you will either come up with an explanation for that, a theory that explains your model, or you'll just be left with a pattern, a law. And we repeat this process over and over, collecting more observations, new hypotheses, more experiments to revise our theories. And again, if we can't come up with a theory, or if we find our theory is too flawed, then we lock our explanation or observation into the form of scientific laws. All right, so let's take a look at the evolution of the idea of elements. The idea of elements started in ancient Greece. One of the first explanations of matter was offered to us by Democritus, and you should know Democritus because one could argue this is where the first theory of chemistry started. Democritus was famous for two things. He gave us the theory of atoms, and he drank a lot of wine. Democritus was a showman, and he presented a lot of ideas. One of the ideas that he presented was that perhaps all the matter around us, all the rocks and water and air around us, if you break it down into pieces, if you take a rock and break it in half, break it into pebbles, break the pebbles into gravel and the gravels into dust, and you keep breaking it down, eventually, he suggested, you're going to get to a piece that you cannot break down any further. And the smallest piece, that smallest kernel, that seed of matter, he called it tomos, indivisible. He explained things like stones by saying they were just made, of atoms packed really tightly together. That smoke and air was basically just these particles not as well connected. He suggested that liquids were, well, somewhere in between. He suggested that heterogeneous matter, like a log, might be a collection of dense atoms and a collection of more disparate atoms, more spread out atoms. Anyway, the theory of atoms, which Democritus offered us, this really is the first theory of chemistry. But we kind of took a left turn. To compete with the theory of atoms, we had elemental theory. Elemental theory was offered to us by Empedocles. Empedocles was a good man, trying to ration and reason and understand the same problem as Democritus. But he offered another theory that one could argue impeded the evolution of chemistry for about 2,000 years. Empedocles offered the theory of elements. He suggested that, well, it didn't make sense to him that the rock was made of the same thing as a glass of water. He suggested there were essential substances that could be combined as mixtures to make wine or different materials. But there were some materials that were so essential that they were fundamental to all other materials. He suggested, for example, that coal might be made of, well, earth and fire, and that by doing a chemical reaction, you could get out the dust or the ash, the earth, or you could get out the flames, the fire. He found those same elements in other places, like, for example, when he put his hand through a smoke, he found what he thought was the same ash from the coal. So he said that earth is in smoke, but so is another substance, which he called air. And water and fire might both be in wine. And you can tell that because, well, you can extract the water, and if you put a match to it, well, the flames come out. He said, for example, wood. Wood was a mixture of maybe all four of those elements. You put a match to wood, flames come out, smoke comes out, air is released from it. What's left after it burns is ash or earth. And he suggested that, well, if you squeeze a log hard enough, water comes out. He suggested that these fundamental substances were just combined in different ways to make all the material around us. Okay, so two competing theories, the theory of atoms and the theory of elements, originally in opposition to each other. The Aristotle came in and weighed in on this and even suggested a fifth element or a fifth consideration that was the space between these elements. But he suggested that fire, earth, air, and water, in other words, he endorsed Empedocles' theory. And, well, Aristotle had a lot of clout, and so we marched forward with a theory of elements. That was the accepted theory. And the theory of atomos, these kernels or seeds of matter, got set aside for, well, about 2,000 years. But the next period in time that went forward, the time of the alchemists, the discovery of elements, of exploring elements, we did discover some fantastic things during that time. Even if we were stepping away from a fundamental truth, that matter is in fact made of these seeds or kernels called atoms. But as we proceeded on elemental theory, well, elemental theory evolved. It changed. We started with the idea of earth, air, fire, and water, talking about some of the elements as being moist or warm or dry, some of the elements as being alive, and some of the elements as being dead, and started exploring how we could work with these essential substances to explain all the matter around us. Other cultures looked at maybe different subsets of matter, but the idea of a fundamental substance was universal. And the alchemists, the alchemists started taking a look at the matter around us and trying to find, well, fire, earth, air, and water in all the substances around us. If you discovered a new brown liquid, one of the first things you did is you tried to break it down. Tried to break it down into simpler materials, maybe a brown dust and a different liquid. And then each with different and unique properties, which made it different than the first one. Not a mixture, but having additional properties or separate properties. And then by chemical reaction, maybe breaking that down to other materials. The alchemists went through and broke down all the materials around them, cataloging their properties, describing how each of these were extracted from other materials around us. But they did find fundamental substances. They found things like carbon or sulfur that couldn't be broken down any further. This is where the idea of what an element is adjusted. We were looking for these fundamental substances, earth, air, fire, and water. But what we found was maybe different fundamental substances, things like sulfur, things like bromine and mercury. Originally, as we started adding to this list of fundamental substances, we started by evolving the elements. Mercury was thought to be the essence of water, a fundamental substance that has in it the essence of the liquid state. Sulfur was thought to be the essence of fire. We called mercury quicksilver back then and sulfur brimstone. And these two elements, two of the first modern elements that the alchemists were able to extract and identify and characterize, they're still on our periodic table. But we continued on that process of trying to find fundamental substances from other materials around us and break them down and characterize their properties and capture their properties. Each new substance, as we identified it, evolved this theory of elements, and we started making a longer list. Paracelsus, who was a famous alchemist who, in some ways, back then, alchemy and chemistry and medicine were essentially one subject called alchemy. And Paracelsus, who made great contributions to both, started trying to organize things into separate columns. He suggested that maybe salt, mercury, and sulfur were these fundamental tracks from which the more classical elements could be derived. And like I said, mercury and sulfur, they're still on our periodic table. Salt, as it turns out, that he thought was maybe the essence of life, in the same way he argued sulfur was the essence of fire and mercury the essence of water. That didn't pan out. Salt, turns out, is a compound, which we'll talk about in the next chapter. But going through and identifying each of these elements, we were able to start understanding, or to start creating models of how the world works. Now, not all those models were completely accurate. No model ever is. But they did improve our understanding of the world around us. As we were looking for fire, one of the things that we observed is that, well, some materials burn and others don't. An organic plant or animal material, wool or paper burns. And once burned, these substances were converted to a lighter material, smoke, soot, and ash. We observed that a candle put in a sealed container or closed container would burn for a while, but then go out. Okay, so those observations led to a hypothesis. Like I said, this is scientific method. You observe what's going on, then you try and explain it. Well, our first explanation of this was that some substances contained the essence of fire, and others don't. And we named that, as we were trying to identify that material, well, we originally named it phlogiston. Phlogiston, we argued, has mass, and it's released into the air when the wood burns and becomes a lighter clump of material. Something left it as fire was released, so we said that fire was maybe phlogiston escaping that material. And the idea that the candle would go out after a while, well, the hypothesis, the idea was maybe this phlogiston was filling the air, and the air could only hold so much. So when it got full of phlogiston, the fire went out. The next step up, after you have an idea, a model, is to test it. So we tested it. One way we tested is we placed a mouse inside the bell jar with a candle. We observed that the mouse passed away. Our explanation for that observation was that respiration was similar to combustion, a similar process, and it turns out it is. Our current models are consistent with that. We suggested that placing a mouse inside the sealed container with the burning candle, and the candle would go out faster and the mouse would go out faster. So we suggested that respiration was releasing the same substance as combustion. There's some flaws in this model, but you start to see how we go from observation to explanation, hypothesis, to testing it, to trying things. We put a plant inside that sealed container, and the mouse and both the candle lasted longer. This reinforced our belief that maybe we were onto something here. And it was further consistent that that these plants that were maybe absorbing this thing that was coming out of the candle and out of the mouse, these plants, which are getting heavier during this process, that maybe that their capturing of this material is why plants burn. Okay, we found that if we put the plant in there for a while, we could then relight that candle. All of these things reinforced our working hypothesis. Okay, now phlogiston was later demonstrated to be a flawed model. This isn't how flames work. It's not how respiration works, but it demonstrates the process of observation, reasoning, and testing. And and here's the thing, even though phlogiston and the theory of phlogiston was eventually shown to be inconsistent enough with reality that we set the theory aside, in its time, it advanced our work with bronze and the refining of steel. By using the theory of phlogiston, we were able to create better smelting, better furnaces, better forges. We advanced the creation of metal. We developed new guns and cannons based on this. Using the theory, we improved the formula for gunpowder, and we were able to develop better tools as a result of this. So what this illustrates here is though theories are never perfect. They're never going to be exactly perfect. However, as you remove falseness from your theory, you get a better working model. And at the end of the day, that's all that counts. The theory that's good enough, that is consistent enough with reality to solve your problems today, it solves your problems today. And that's what science offers. Science doesn't offer you perfection. Science offers you a new model, a new way to explore things. So if you look at scientific method, this idea that some substances contain fire and others, some substances burn and others don't, and that the idea that this is because that substance contains fire, that's a hypothesis. A candle in a sealed container that burns and could later be restarted. This is an example. This is us observing what's going on. Placing a mouse inside a sealed container with a burning candle. What do you think that was? Was that a hypothesis, an observation, or was that an experiment? You should be able to describe each of these pieces: hypothesis, observation, experiment, refined hypothesis, and identify them because you're going to be using this tool, this scientific method in class. And all of these models that came from all these observations that came from working with phlogiston, understanding what's an observation, what's an experiment, what's a hypothesis, and eventually what's a theory. This is key to advancing your understanding of the scientific method. All right, now after phlogiston, in exploring phlogiston, we discovered still another element. For example, the discovery of oxygen was a consequence of the theory of phlogiston. Joseph Priestley, an English alchemist, who at the time was, who, for example, developed the rubber eraser, seltzer water, gave the rights to a neighbor called Schweppes, hence Schweppes seltzer water. He discovered oxygen. He firmly believed in the theory of phlogiston, but he, being a good scientist, he tested it. He tried to explore it. Priestley's work in trying to demonstrate the truth of phlogiston helped him to understand that phlogiston was a flawed theory. Again, key to science. I mean, lawyers and scientists both seek proof. They look for arguments. But a lawyer starts with a claim that he wants to make. My client is innocent, or this person has committed a crime. And then they try and build a case for it. Science goes the other way around. We don't know whether the client is innocent or guilty. We don't know whether a crime has been committed or not. We don't know if phlogiston is true or not. And we come at it with a humble mind. We don't try to prove as a verb. We try to identify proof to guide our beliefs, to guide our certainty. We try to discover. And that's a fundamental difference. And this is how we discovered oxygen. Priestley attempted to produce dephlogistated air, basically remove phlogiston from air, to get nice pure air, so that you would be able to work with, so that you'd be able to have a better forge. You'd have to be able to use a better fire. Anyway, as he went through and he was exploring things, one of the things that he found was that when you take mercuric oxide and you put it in that jar and then you hit it with a light beam, the flame burns brighter. And so the first thought is, well, maybe this is improving. Maybe this is removing the phlogiston. But here's the thing: the mercuric oxide actually loses mass. It's putting something into the air, not taking something out of the air. Now, this idea that there is better air than air, that you could tune the properties, that you could have something, quote unquote, pure air doesn't exist, but if you had pure air and you were able to tune it, make its properties more acute, then there's something going on here, because a pure substance has fixed and never-changing properties. What you're talking about here is adding something to air, or that property of combustion or allowing combustion isn't air. It's something else in the air, something you could get from the mercuric oxide. So for 23 uninterrupted centuries, one of the most firmly held beliefs that humans had was that air was this fundamental pure substance. Priestley demonstrated the thing we're breathing every day, it's actually a mixture of different things. And that this mixed matter, and like I said, he came at this with a firm and a convinced belief. Anyway, this was about the time of Robert Boyle. Robert Boyle introduced an idea to alchemists, the idea of the empirical method, scientific method, going through and letting the numbers talk to us, letting us discover the material around us. And Robert Boyle published a book called The Skeptical Chemist. This is the first time we started using the word chemist instead of alchemist that I'm aware of. And in this case, he argued that if we want to truly discover new materials, discover science, that what we need to do is we need to take careful observations and let the numbers talk to us. One of the best advocates of this method, although he always called himself an alchemist, was Antoine Lavoisier. He went through and he was engaged in the theory of phlogiston. He also went through and categorized other other substances. And he was famous for taking really precise measurements and using those measurements as an effective argument. He went through and he was able to not only categorize and isolate and categorize many elements, but he collected the works of others, and he created a list of about 33 elements that are the first modern elements. This included different types of elements. He included metals, which were thought to be a different kind of substance for the longest time. Metals and non-metals, elastic fluid, and again, earths. Earths are still on our periodic table. But he built this list, and he started us applying scientific method. So as we started looking at this theory of elements and the elements around us with scientific method, with observation, hypothesis, and experiment, it continued to refine our understanding of the matter around us. One of the first key observations was and the law that came from it was the law of conservation of mass. This is also known as Lavoisier's law in France. Lavoisier's law, or the law of conservation of mass, was a consequence of a very careful measurement of experiments that Antoine Lavoisier did. One of the things we thought at the time was that you could, destroy matter. I mean, for example, when you take ferrite or magnetite and you throw it in a pot, you bring some great rocks out of the earth, heavy rocks. You toss in a fistful of carbon or coke, and then you add some fire to it. Earth and fire gives you metal. And this is how we smelted or we produced iron and copper and other metals. But we always lost mass when we did this. We seemed to lose mass. So we thought that process, which at the time was known as reduction and is still is reduction today. But the word reduction came from the fact that big rocks got turned into a very small amount of metal. But one of the things Lavoisier observed is he said, I don't think that's what's going on here. He tried to reproduce many of these reactions in a sealed container. For example, he might react acid with the sodium carbonate. And you might see, if you do that on a scale, the flask actually loses weight. But if you do it in a sealed container, where in a sealed container, you will see that the reaction actually does not lose weight. That any chemical reaction, if you carefully capture and isolate all the products that come out of it and weigh them, and then you weigh all the reactants that went into it, matter is neither created nor destroyed. And in a chemical reaction, it just gets rearranged. It just gets transformed into other materials. Anyway, the law of conservation of mass, or Lavoisier's law, was one of the first laws to help us. One of the things that helped us eventually get back to theories of atoms. A second law, the law of constant composition, also known as Proust's law. This one is trying to understand different substances. So all samples of a given compound, a material that has more than one element in it, a pure material, not a mixture, but a pure material that is composed of more than one element. One of the things that Joseph Proust observed is that the ratio of elements within it is always constant. For example, if you form this lead sulfide may be formed from, say, 10 grams of lead and 1.55 grams of sulfur. I mean, if you double the lead, it'll use up twice as much sulfur, but the ratio of lead to sulfur is always the same. And if you do the reaction with maybe a little extra sulfur, well, then you have a little extra sulfur left over. The compound that is formed is always that same ratio of 10 to 1.55 by mass every single time. And if you do it with a little bit more lead, well, then you have lead left over. But the compound you form always has that constant composition. And if you think about this in another way, water, for example, water is 88% weight by oxygen, 11.2% oxygen. Salt is about 39% weight by sodium, 61% of chloride. every single time. And it doesn't matter whether you find the water in Paris or New York, whether you find it on Mars, water will always have that composition. At least that was our observation. At this point, we didn't have an explanation as to why. But we did find that everywhere we found water, if we analyzed it carefully, it always had that ratio. This is the second law. This is the second law that goes into our model of atoms. Now, these observations led to a law of chemistry. And again, a law is not a theory. It doesn't tell you why this is the case. It just tells you that every time we've made an observation, without exception, this pattern has been upheld. All right, so these are two of the laws of stoichiometry. The third one was offered to us by John Dalton. Now, the first one, like I said, just says in a chemical reaction, whatever goes in, the same mass comes out. The law of constant composition says that when you have a pure substance, a compound, the ratio of the two elements within that compound are always the same for that compound. The next one is a little bit harder to see. This one is about related compounds. So, for example, I can make mini compounds out of hydrogen and oxygen. I can make water. I can also make hydrogen peroxide. They will have a different ratio of masses of hydrogen and oxygen within them based on Proust's law, and that's part of what makes hydrogen peroxide different than water. But there is a relationship between hydrogen peroxide and water, and this is what John Dalton talked about. So, for example, if you look at compounds that are made of nitrogen and oxygen, I can give you four right here: dinitrogen oxide, nitrogen monoxide, nitrogen dioxide, nitrogen tetroxide. All of these different compounds have a different ratio of nitrogen to oxygen. But if I make each of these compounds from 1 gram of nitrogen, and I pay attention to how many grams of oxygen are produced, well, still doesn't seem to be much of a pattern, eh? I mean, the amount of oxygen is very different in each of those. It'll always be the same for that compound because of Proust's law, but two different compounds will have two different ratios. But here's the trick. Here's the thing that Dalton observed. If you compare the mass of oxygen in one of those compounds to the mass of oxygen in the other for the same mass of nitrogen, the ratio of oxygen in between those two compounds is always a small whole number multiple. Okay, think about this for a minute. If we're just blending these things, if we're just making two different kinds of pancakes, and yes, maybe one of them needs a little more sugar and the other needs a little bit more milk, but why would it be quantized like this? Why would the relative oxygen between one compound and another compound be different, but be a whole number multiple? All right, this is and these ratios are very consistent. You know, between nitrogen monoxide and nitrogen dioxide, well, the ratio of oxygen there is 2 to 1. And if you go down here, it's 4 to 1, 8 to 1, 2 to 1. It's always some small whole number multiple between two entirely different compounds. Again, these are observations. And so this led us to a third law of stoichiometry. When two elements, call them A and B, form two different compounds, masses of element B that combine with 1 gram of element A can always be expressed as a small whole number ratio. So again, the amount of oxygen I need for the same nitrogen in two of those compounds is always going to be some small whole number multiple of each other. All right, so this is Dalton. This law of multiple proportions was offered to us by John Dalton. Now, John Dalton took it to the next level. John Dalton was a school teacher. What he explored is he's trying to understand chemistry. He looked at these laws that both the laws that he had captured and shared with the world, and that Proust and Lavoisier captured, and he went one better than a law. He combined these laws and he offered an explanation that became one of the most fundamental, arguably the most fundamental, the first law, or the first theory of chemistry. So what he suggested is, well, if I always need some fixed quantity of oxygen, say with 1 gram of carbon to form these compounds, maybe it could be a 1.33, it could be 2.77, but whatever it is, every carbon and oxygen compound is going to have some multiple of that. That means that maybe this mass is combining in small packets or chunks, reminding us of what Democritus said, right? And that each of the particles, for example, that make up carbon monoxide might have 1 part carbon, 1 part oxygen, but in these fundamental units, carbon dioxide, 1 part carbon, 2 parts oxygen, but in these fundamental chunks or packets. This is what brought back the theory of atoms, the first theory of chemistry, which eventually came back to us thanks to John Dalton. I mean, we had been categorizing the elements. Lavoisier made that list of 33 elements, characterizing their different properties. What John Dalton suggested that the elements themselves are composed of atoms. The smallest particles. He borrowed the word from Democritus atomos. That all of these fundamental particles of any given element, whether it's carbon or oxygen or fluorine, all these particles are the same. However, a particle of carbon is going to be different than a particle of oxygen. For example, the oxygen weighs more than the particle of carbon. The whole idea of diatomic particles was a bit of a difficulty for John Dalton, but Amadeo Avogadro actually helped him crack that particular puzzle. But this idea that matter or elements came in these small particles, this brought us back to atomic theory. Now, all the stuff we'd learned about from elemental theory helped us understand these different flavors of atom that John Dalton were suggesting. He suggested that you can create different compounds from the elements because you're combining these fundamental packets in different ways. You can't change one element into another, he argued, and for the most part, you can't. So when you're doing chemical reactions, if you have carbon and oxygen and nitrogen going in, you're going to have carbon, nitrogen, oxygen going out, but you can recombine them in different patterns. Maybe I can take some materials that are pure carbon and pure oxygen, and I can mix them to form particles where I've got 1 carbon with 2 oxygens, or in a different reaction, 1 carbon with 1 oxygen. And these patterns of how these chunks come together, these ratios of how they come together, are the identities of the compounds that can be composed from the elements. All right, so this brought us back to the theory of atoms. And we're going to talk more in our next lecture about atoms and get into some more of the details of that. But we discovered atoms by exploring the elemental theory and coming back to it. Now, as we start talking about these flavors of atoms, as we started getting more and more elements out there, 4, 16, 33, as our list of elements got bigger, these very ornate symbols that represented each of the elements of air, earth, water, and fire, and then gold and mercury and sulfur, as we started developing more and more of these. These ornate symbols became cumbersome. So what we did was we decided that we would use as symbols something simpler, something that can be used and set in type. We used the first letter of the name of each of the element. So hydrogen is symbol is just H. Carbon's symbol is just C. Phosphorus is just P. Now some elements share the same first letter. So when we got the helium, we had to say, well, we can't use H because that's already been That's already been used. So we are going to instead use HE, 2 letters for that. And some of the elements on the periodic table actually have three letters in their symbol when you get down. But for the most part, the elements are represented by a single or by two letters. When you write these elements, the first letter is always capitalized, without exception. And the second and the third, if it's there, is always lowercase, without exception. Okay, you're going to be responsible for not all the elements, but you are going to be responsible, just so we have these tools and are able to have discussion, for the first 18 elements. So you should take a look at in Canvas, there's actually a game, a set of flashcards you can use to explore and to start matching the names and symbols of the first 18 elements. And it'll give you a random collection of 8 each time, so you can play this game over and over again. And that may be useful to you to start understanding the symbol to the name for each of these elements. Now, this is what science did. We started organizing these things, giving them names, giving them symbols, and then we created our own set of flashcards for this. On each card, we put the symbol, the name, and the relative weight of this element. And we would use these cards to kind of organize ourselves. And like I said, when we had 4 or 16, well, that's fairly easy way to work with it. But when we start having 33 and more elements, we need to get organized by it. So we gave them a serial number, the atomic number, which originally was just a serial number. It ranked the elements in order of increasing relative mass, kind of like the way you might organize a hand of playing cards. You basically collect all the cards and you put them in order, maybe of increasing order, so you can find them as your hand size gets larger and larger. And our hand size got larger and larger. I mean, we didn't just have 16 and 33 elements. We got up to 52, 54 elements. But here's the thing. As we got more and more of these, this line of flashcards that we created, each serialized with a number, one of the things we noticed is that certain properties repeated themselves, kept coming back. This is the law of periodicity. The law of periodicity says that as you lay out the elements in a line with according to increasing mass, you will periodically see the same property repeat itself. For example, fluorine, chlorine, bromine, each of these materials, as we go in increasing mass, have very similar reactivities with other substances. The compounds they produce have similar patterns in them. If you take a look at helium, neon, argon, krypton, each of these gases, which for the longest time we didn't even think existed, there was a lot of argument as to whether the helium, neon, argon even were really elements. These things are very unreactive. They don't do anything. They're all gases at room temperature. They're almost completely inert. There's only a handful of compounds we've made from all of them combined. And you take a look at the metals like lithium, sodium, potassium, cesium, rubidium. Each of these metals is a shiny, malleable, lustrous metal that explodes rather dramatically when you mix it with water. Okay, so this law of periodicity, we seem to find that basically Mother Nature repeats itself periodically as you go in order of increasing, as you start laying out these cards. So, I mean, how would you organize your cards if you saw that repetition of a pattern? I mean, have you ever laid out a set of playing cards going ace to king and then maybe switch suits, ace to king again? This is what we did with the periodic table. We used this table of elements, and periodically we wrapped it around again where those properties repeated themselves. This is how we created the periodic table. This is why we call it the periodic table. All right, and again, you're responsible for the first 18 elements so far. So take some time to make sure you know their names, know their symbols. Make sure you can find them on the periodic table, all right? You will always be able to use a periodic table when you take quizzes or tests in this class. You can download the class periodic table by clicking on the references link in Canvas. You can download it as a PDF, print it out. You can always take that sheet of paper with you into tests and quizzes. And if you're taking future chemistry classes, there'll almost always be a periodic table hanging on the wall. Periodic tables and Bunsen burners are iconic tools of chemistry. And you're part of the club now, so these are your tools too. All right, now next up, how that periodic table evolved. You can't talk about the periodic table without talking about Dmitri Mendeleev. Dmitri Mendeleev, another school teacher like John Dalton, was probably one of the most vigorous defenders of the law of periodicity, and he was such an advocate of it because he used it, because he tried to break it more than anyone else, but he found in it a logic, a dependable pattern that we still weren't able to explain at the time. But that pattern was so consistent that he firmly believed that this law of periodicity could be used, could be relied on, could be trusted, simply because we'd never seen an exception in 2,000 years before that. Anyway, so when he laid out his periodic table, unlike other folks who laid out their tables and wrapped it around and tried to match up the periods as best they could, well, when he couldn't match up the periods, he left holes in his periodic table. He made sure that that iodine was in the in that same column with fluorine because the similar chemical reactivity. Other people actually disagreed with him and thought tellurium should be in that row and iodine in the row before, because if you order things in order of increasing mass, those two tiles actually should be replaced. But the law of periodicity told him there was something fundamental about iodine and bromine and fluorine and chlorine that linked each of these things. Their chemical properties were so similar, and he was such a strong believer in this that when somebody he actually suggested elements that didn't exist yet. In these holes, for example, under aluminum, he said there was a substance that we would discover someday that he called eka-aluminum, after aluminum. And he predicted the properties of it based on the properties of aluminum and the elements in that row and his understanding of the law of periodicity. And when gallium was discovered, the person who discovered it published its properties, and Mendeleev wrote him a letter and said, "I think you got it wrong." And the guy said, "What are you talking about? I'm the only human being who's ever seen this element. I painfully extracted it." And Mendeleev said, "Yeah, but the law of periodicity suggests different properties. I think you made a mistake. Go back and look at your data." The guy did, and he eventually published a correction. Mendeleev was right. Like I said, before gallium was even discovered, Mendeleev was able to predict its atomic mass, the density of the material that we found, its melting point, the oxides that formed from it, the chlorides that formed from it. He was able to predict the chemical reactivity and the physical properties of this with great accuracy. Also, he predicted it for germanium as well, which he called eka-silicon, again, after silicon. And his predictions, perfect. Man, those are very close predictions. Anyway, Mendeleev's periodic table was probably one of the best of its time. And as we added more and more elements, we started with 4, then 16, 33, 54. We just kept adding to this thing. As we started, putting space where elements weren't found, we started finding that we had to stretch this periodic table quite long before the law of periodicity suggests we should wrap around again. This became quite cumbersome. So one of the things we decided to do is the elements on either side, the elements in the first two columns and the elements in the last six columns, very well behaved elements. And the elements in between get a little bit weird. But you see that gap where the green tiles are, where there's nothing above them? Okay, to make this whole thing a little bit more compact, we cut those inner elements out of the yellow block, which is the transition metals, and we placed them below the table. So we cut the inner elements out of the transition metals, and we called them the inner transition metals. And that made our periodic table a little bit more compact. It's a little bit more cumbersome, and frankly, we're going to have to do this again as we are likely going to extend our periodic table quite a bit more in the next few years. But this structure is what gave us the periodic table we have now, where each one of those horizontal rows is a period, each one of the vertical columns is a family of compounds with related properties like fluorine, chlorine, bromine, iodine. And yes, that lanthanide and actinide series, those brown ones, they fit right into that yellow chunk, and it really should be a wider one, but it doesn't fit on the paper as easily that way. And as you see in that last row of the periodic table there are three gaps. Those three gaps were the last of those three gaps was filled in 2015, December of 2015. I remember quite well. We popped champagne. Chemists are geeks. What can I say? Bottom line is we celebrated the completion of Mendeleev's vision, and here's the thing. Again, Mendeleev didn't define this. He helped us discover it, and there is a difference there. But this vision that Mendeleev had turns out to be the one Mother Nature had a long time before Mendeleev. He was just able to see it in the tea leaves and help us see how these elements fit together. Anyway, this is the chemist palette. Chemists create or synthesize or extract. Chemistry is the science of matter. 183 million different types of matter that human beings are aware of. And it's all made from these 118 flavors of particle. All right, now you should know how to navigate this periodic table. You'll always have a periodic table with you to work on, but you should be able to, you should know how to navigate this table. One of the ways that one of the first divisions here are the metals and the nonmetals. Again, for the longest time, we thought metals were something fundamentally different than elements. We're wrong. They're elements. But the vast majority of this periodic table, all those yellow tiles, those are the metals. Metals are found on the left and lower end of the periodic table. The green tiles in the upper right-hand corner are nonmetals. And the reason, the way we characterize these is by differences in properties. All of the metals share properties of being ductile, which means if you grab them and pull them, you can pull them, stretch them into a wire. They don't break, they don't crack, they just reform into a wire. And they are also malleable. When you apply pressure to them, they don't fracture and crack like glass, or like solid sulfur or solid iodide will crack when you apply pressure to it. But metals deform. That's how you can stamp a symbol in a gold coin, or you can press iron. You can bend iron if you apply enough force to it, as opposed to more brittle substances, which are the nonmetals. They're also conductive, and it's a fair question to say, what do you mean conductive of? Electricity or heat? And the answer is both. Metals have a property in that they conduct heat and electricity extremely well, and we'll talk about why in the near future. So they're great conductors. They're malleable. They are ductile, and they're shiny. Metals catch our eye. They are shiny. They're also solids at room temperature, and they have very similar properties. And all of these properties of metals increase as you go to the left and go down, roughly. I mean, there's some exceptions and bumps in the road, and they decrease as you go up and to the right. And again, you'll notice that most of the tiles on this board are a metal. If I gave you an element at random, odds are it would be metal. So if someone says, say on a test, if I give you a tile off the periodic table at random, is it more likely to be a non-metal or a metal? They're asking you, of the 118 elements, which ones do you find more of? The answer is the metals. By the way, do you see boron there, and then aluminum, silicon, that little staircase in purple between the metals and the non-metals? Those 7 elements are the metalloids. There's something that has properties somewhere between a metal and a non-metal, with the exception of aluminum. If you go down that stair, down and over, down and over, down and over 7 times, that identifies the metalloids, with the exception of aluminum, which is right under boron, and aluminum is unquestionably a metal. So what is a metalloid? It's something that has properties sort of like a metal and sort of like a non-metal. I mean, when it's something that is sort of a conductor of heat. It's sort of malleable. It's a semiconductor of electricity. In fact, the semiconductor industry, when they first started building this, they argued they could build semiconductors. They could build chips out of silicon, germanium, or arsenic, and they ordered pure quantities of all 3 elements. And the fact that silicon got here first is the only reason why the first chips and most of the computer industry is based on silicon. And personally, I'm grateful for that, because if FedEx had got arsenic here first, I'd be in the middle of Arsenic Valley instead of Silicon Valley, and I think Silicon Valley is a much catchier name. Anyway, these are the first categories of elements: metals, nonmetals, and 7 metalloids. Other regions of the periodic table, like I said, the first 2 columns and the last 6 columns, the ones in blue here, those families of elements, those 2 blocks combined, they're known as the representative elements, and they're very well behaved. They represent the periodic law quite well. They represent the families in which they're found quite well. Those are the representative elements. The yellow ones in between, those are the bad boys. The yellow ones in between, that's the wild, wild west. All the rules break in there. And the inner transition metals, the ones inside those yellow transition metals, the metals that transition from the representative elements on the left to the representative elements on the right, those inner transition metals, man, we're just starting to figure out their logic. If you're looking for research projects, there's a bunch of them. Now, each of the columns in those representative elements, they're families. Like I said, if you look at fluorine, chlorine, bromine, and iodine, that, like I said, Mendeleev had to fight for. Most people wanted to put tellurium in that column. All of those are families. And I don't know, in your family, do you have a lot of the same likes as your cousin or your brother? Do you play some of the same games? Do you enjoy some of the same music? Well, it's the same thing with elements. Within the families, there are some commonalities. And so it'll be useful to identify which family a particular element is in. Now, the first column that includes lithium, sodium, potassium, rubidium, cesium, these are the alkali metals. These are the metals that when you throw them in water form alkali solutions. In other words, we'll talk about alkali in the second semester. But these are the alkali metals. You should be able to identify them. The second ones, these are the earths. I told you there's still earths on the periodic table. These are the alkaline earth metals. Their properties are different than the first column. Like I say, the transition metals are weird. They do some weird stuff. If you go all the way over to the other side, to the other side of the periodic table. Those are the noble gases: helium, neon, argon, krypton. Like I said, for the longest time, these weren't even on the periodic table. We didn't think these elements, I mean, there was debate whether these elements actually existed, because the way we demonstrate that an element exists is by measuring its properties and its chemical reactivity, and there's zero chemical reactivity there. In 2,000 years, we've got like a fistful of compounds that we've been able to crunch out of those, and for the most part, they are just inert. That's why we call them the noble gases. They just kind of sit there and stare at us and don't do any work, like nobles. Anyway, and then the next column over, that's the halogens. The halogens, now this is the working class materials. Fluorine, chlorine, bromine, iodide. You get a lot of chemistry out of this stuff. But the halogens are that column right before the noble gases. The column before that is the chalcogens. Oxygen, sulfur, selenium, rubidium, tellurium. These are the chalcogens, and you should be able to identify them. The next columns over, those three columns over, I'm not going to hold you responsible for, but the nitrogen, phosphorus, arsenic column are known as the pnictogens. It's spelled weird. P-N-I-C-T-O-Gen. But take a look. The first elements are phosphorus and nitrogen. Pnictogen. It's easy to remember. The next one over is probably the most important one, but it's also got the most boring name. It's got the most complex chemistry, but the most boring name. Carbon and the stuff underneath it is known as the carbon family. Not surprising. The one after that, boron, aluminum, that's the poor earths or poor metals, and that's because those poor metals have properties that are poorly the properties of metal, or not good properties of metal. Anyway, you are responsible for knowing the families alkaline metals, alkaline earths, noble gases, halogens, and chalcogens. And you also, just to be clear here, those are the columns, the vertical columns, the families. The horizontal rows are the periods. Periodic table, right? Each time you have a new period, you wrap it around. The first period contains only two elements, hydrogen and helium. There's only two first period elements. And the second period starts with lithium, beryllium, boron, carbon, nitrogen, oxygen. This is the second period. And then the third period is the one below that, and so forth, going down. So be careful. Like on standardized tests, they will frequently ask you, what is the second period halogen, as an example? A lot of people would look at that and they say, okay, well, the first halogen is fluorine, the second one is chlorine, so I'm going to put chlorine as my answer, and they're going to lose points. Because they're not asking you what is the second halogen, they're asking you what is the second period. To identify an element by its family and its period, you have to imagine this is a grid with all of those tiles filled. And so when I say the second period halogen, the answer is fluorine, because there is no first period halogen. All right, so this is the periodic table, and like I said, you can download the class periodic table from Canvas. Go into the references, it's linked from the first page, and there's a bunch of tables there, most of which you won't need till the second semester. But the first one in the list is the class periodic table, and this is literally a photocopy of the inside of our textbook. And if you're using the electronic version of the textbook, this is probably the easiest way to get a hold of that periodic table. Now, there's some numbers on there, and there's a lot of secrets in the periodic table. The periodic table is literally the best cheat sheet you will ever have. I guarantee you that. And it's the only one you get to use on quizzes, tests, etc. But that's cool. I'm going to show you a lot of tricks. I've shown you a few of them now. There's a lot more still coming. But download this as a PDF, print it out, and keep a copy of it. And every time you go into a quiz, this and some blank sheets of scratch paper, a pencil, and a calculator are what you're allowed to bring in. All right. That's it for now. I will let you go. If you guys have any questions, ask them on the forums or shoot me an email, and I will let you go. And I hope you have a wonderful weekend. Bye-bye.